Okay, folks. This is Mr. Heier. Today we're going to talk about free fall. We're not. This is what we're going to do over the next couple of days. Really, isn't anything new. We're just looking at a special case of what we've been talking about: accelerated motion. Okay, so something that's in free fall, okay, is something that the force of gravity causes an acceleration that is directed towards the center of the Earth. Right. So the only thing that is pulling on something that is in free fall is gravity. Okay? Objects affected only by gravity in free fall. So some examples, right? Football in midair, skydiver, tennis ball being thrown upwards. In all these cases, in the real world, there's air resistance, but we're going to ignore the air resistance in these parts, right? So as they're falling, we're saying they're in free fall. Now, if an airplane is flying, an airplane has gravity pulling down on it, but it also has a lift force that makes it fly. So gravity isn't the only force, so it would not be in free fall. All objects accelerate at the same rate when they fall vertically. Galileo, long time ago, was able to show that. Right? And in the absence of air resistance, everything is going to fall at the same rate. Right? Seems weird. If I drop a feather and a hammer, obviously the hammer is going to hit the ground first. That's because air resistance gets in the way. So if we could pull all of the air out, we should be able to show that they fall at the same speed. Well, that's hard to do, but if you go to the moon has no atmosphere, no air resistance, and the feather and the hammer should land at the same time. So I'm going to show you about a minute and a half video here that this actually happened back in one of the Apollo missions. Right. So the feather and the hammer do go at the same time. We don't see it in the real world because of air resistance. Right. So we've been studying motion, acceleration, velocity, displacement in one linear dimension on the x-axis, horizontal, basically. Right. Cars moving back and forth, people walking, forward and backward, north, south, things like that. Right. So if we're talking about gravity, we're going to be describing vertical motion, y-axis acceleration. Okay, and gravity, of course, acts down, so that's going to be the negative direction. Right? But the acceleration due to gravity is going to describe the vertical motion. Right. So the acceleration due to gravity on the Earth is 9.8 meters per second squared, downwards. Right? We give it a special letter. We call it g. Right? And g is negative 9.8 meters per second squared because it is down. Right? So in other words, every second that goes by, over 1 second that goes by for free fall, it's going to increase the speed by 9.8 meters per second. Right? If I drop something, the initial velocity is zero if it's dropped. Right? So G is our symbol for the acceleration of gravity. Right? G can replace A in our acceleration equations that we learned. And we're going to talk about each one of those when an object is in free fall. Right? G is always negative. Okay. Although sometimes we may use it as the absolute value of that is positive when we're calculating time in certain situations, but we'll get to that if we need to. Right? So if I throw something in the air or if I drop it, this is the equation that we can use to find the distance that it goes up or that it falls downwards. Right? Remember, this was just d equals VIT plus 1/2 AT squared. We're just replacing the A with G, right? And we're writing a Y here because it's in the Y direction. Right? So dy is the vertical displacement. So if we were talking about horizontal displacement from now on, we might talking about being dx. Right? But if I drop something, what's my initial velocity? Isn't vi, sorry, isn't my vi just 0? And so wouldn't this be 0 and this whole term go away? So when we drop something from rest, we can really just say that the distance that has fallen is 1/2 gt squared. And you're going to get a negative number for dy because it's going down. We already talked about that. For an object in free fall, we can use this equation to find the time or the final velocity. Remember, Vf equals Vi plus At. In place of A, we just use G. These are not new equations. We already know how to use these. We've already used them. And if time isn't part of the question, we can go back and use the one without time. And of course, we replace A with G, and this is what we would use in free fall. Right, now, important, those last two equations only work if you're talking about something going up or going down, a one-way trip. When we start talking about it going up and down, we're going to have to be smart about it. Okay? If the object is in free fall going up and going down, we'll have to adjust our time. But we will talk about that later in another set of notes. All right, so let's look at a couple of examples. Okay, so Anne jumped off of a diving board and landed in water in 1.25 seconds. How high was the board? All right, so like we did before, let's write down what we know. She jumps off the diving board, just drops right off, then VI is going to be equal to 0, right? So we're going to say VI here is equal to 0. V, we don't know. We don't care at this point. Right? The time is 1.25 seconds. My acceleration is g, or negative 9.8 meters per second squared, and it's my distance that we're looking for. So we just plug in VIT plus 1/2 GT squared. Of course, this again is 0, so it's really just 1/2 GT squared. That should be a plus. And so my dy is negative 7.66 meters, which means it fell 7.66 meters. So really, the height would be a positive number, 7.66 meters. The dy is the displacement that it went downwards. Okay, second example, you drop a golf ball. Oops, sorry about that. You drop the golf ball off the bleachers. It falls for half a second. What velocity does it hit the ground? All right, so this time, again, if I drop it, I know that VI is equal to 0. I know my acceleration is equal to g, which is negative 9.8. All right, what else do I know? We know the time is 0.5 seconds, and we're looking for V final. Right, so if we look, this is our first equation, V equals VI, or VF equals VI plus GT. Right, this was AT, but now it's GT. Well, we just plug our numbers in. Right, so VF is going to equal to 0 plus negative 9.8 times 0.5. So my V final is for negative 4.9 meters per second, which means it's moving downwards. That's what the negative sign means. How high were the bleachers? This time now I'm looking for dy, and I can use my dy equals 1/2 gt squared, because again the initial velocity is 0. So 1/2 times negative 9.8 times 0.5 squared, and so my dy comes out to be negative 1.225 meters, which means the height was 1.225 meters, and that's fine. We can use that as my answer. All right, this is another problem. This is not in your notes. You might want to write it down or just try to do it on your own. Hit pause and try to work through it. Okay, so that Six Flags popular ride known as Free Fall carries passengers up to a height of 33 meters and drops them to the ground inside a little cage. How long does it take it to fall? Okay, again, what are my givens? We know that my dy is negative 33.5 because it's going down. We know my acceleration is g, or negative 9.8. We know my initial velocity is 0, and I'm looking for the time. Right? So my equation is going to be that one, right? The second one, but remember that that's going to be 0. So it's really just dy equals 1/2 gt squared. Right? Then we can just plug in our numbers. It becomes negative 33.5 equals negative 9.8 t squared. The negative signs cancel. We get t squared equal to 6.837. And then, of course, we take the square root of both sides. And we get our final answer to be 2.61 seconds. All right, just like the problems we've been doing, now the things are just going up and down, or in this case, just down. And later, we'll look at them. We'll look at them later going up and down. But right now, they're just going down.